Okay, the second half of the year, I know some grades do it earlier and some don't, it depends. But let's say the module that comes into the second half is where we're going to start looking at electricity. Okay. Now, first of all, we're going to break it into, let's say, two sides, just for the time being. The first side is electrostatics, where we've got, let's write, static electricity, right? We're going to look at charges on spheres. We're going to look at when we put them together. But more importantly, we're going to look at the forces that actually interact between these things. Why are we doing this? Well, because in many aspects of life, forces that we can exert on electrons will give us things that we can use. We can, for example, change the paths of electrons. If you go to the old cathode ray tubes, ancient TVs and things, they were in there, that we could change the path of an electron. And that's what we're going to be looking at. So the other side of it is going to be the electricity that we look at in circuits, where we look at batteries, we look at resistors, we look at various bits and pieces, and essentially we solve the circuit. We look for the bits that are missing. Right? Let's look at the first part, which is the electrostatics element of it, where we've got some static electricity. This is for, I've got a very nice example in there. We've got a static electricity situation. Now, we know, or you know by now, that obviously we could have a situation where we could have a positive and a negative charge. And you know that these two are going to attract. A positive and a negative would repel. We know, for example, that two electrons don't really want to be together, a la the whole chemistry process. They sit on the outside of the s orbital, remember? They sit on the surface. They try and be as far away as possible. That's pretty much the same with electrostatics. All the charges sit on the outside. If we go back, do you remember how we got these charges? We took a glass or a perspex rod, or I think the one was called ebonite or plastics or whatever it was. We took those and we took a cloth and we wiped the cloth across it, didn't we? Right? Well, what did we do? We actually took electrons and wiped them off, didn't we? So let's think about it as it's a transfer of electrons from one place to another. So we're taking electrons away and we rub it and we deposit electrons over here. A whole bunch of these guys. Right? Now, obviously, each electron that we've got there has got a charge of minus 1.6 times 10 to the minus 19 coulombs, which is our base charge, isn't it? So if we move 10 electrons, I'd multiply that by 10, wouldn't I? Okay. So what's important for us to remember, not only for the physics but for chemistry later, is that electrons are being moved. And the total charge that we build up depends on how many electrons we've moved. So we could say the total charge that we put onto this element here is going to be 3 times minus 1.6 times 10 to the minus 19, and that's coulombs, isn't it? So can you see what we've got here? And it's part of what we need to develop is the total charge. The total charge that we define is Q, and it is in coulombs, right? And what is it? Well, it's the number of electrons times the charge on an electron, isn't it? That's how many coulombs. So if I wipe off 10 electrons and put them on there, I've got 10 times that is my total charge. Similarly, on this side, we've got plus 10 times that because we took 10 away, didn't we? That's fairly straightforward, but very often it's something that's forgotten. I just wanted to revisit it so that we can use it as we move ahead. Let's just look at the next piece of this. Just recapping, some of you have done it, some maybe not. If we've got a charge, let us say on these lollipop thingies, we've got our charge there and we've got our charge there, and on this one we've got a charge of let's say minus 10, and on this one we've got a charge of plus 20. Never mind what coulombs there are for the moment. Okay. What are we saying? We're saying that on this side we have got electrons, right? We've got 10 of them. 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are sitting on there. And remember, they sit on the outside surface of your ball or sphere or whatever it is. They sit on the outside because they try and move as far away from each other as possible. This side, we've got 20 positions that can be filled by electrons, haven't we? Because this one is 20 electrons short. 1, 2, 3, 4, 5. There we go. I'm just going to draw 10 and say times 2, right? Now, what happens here? Let's just look at it and we say, well, first of all, positive and negative, which means that there's a force of attraction between the two, isn't there? Why? Because this wants its electrons back. Okay? Now, okay, what happens here is that we've drawn pretend field lines. You've all, I'm sure, taken a magnet, one of these guys, put it underneath a piece of paper or cardboard and sprinkled iron filings and given it a shake. And you get the magnetic field, don't you? Well, we are doing it. Essentially, we're drawing this as a diagrammatic representation of this being positive, this being negative, and those there are, come here, I want you next to me, because they are attracting each other. Okay? Now, first of all, we always note, number one, we draw the lines from plus to negative. Okay? Always. And in this case, you can see that it wants to bring it closer, doesn't it? So we draw the lines from positive to negative. Similarly, if we had magnetism, we draw from a north to a south pole. It's just an indicator. It's arbitrary. It's what we've chosen to do. Okay? No reason why. Well, not that I'm aware, but there might be a reason why. We don't even need to know. So we're going to draw the lines from there to there, right? So in any theoretical situation that you get, right, they could, for example, say to you, here we go, I'm going to draw sphere A and sphere B over here, and they say it does this. Well, what do? They want to know what are the charges. Firstly, we look at this one. These are trying to push each other away. So we say it's repulsion, isn't it? Right? So if this one is pushing away, the next thing we look at the direction of the arrows and we say, aha, it's drawn away from here, which means this must be a positive and a positive. That would give us repulsion, positive and positive, wouldn't it? So we always draw them away like that in this case, right? That we look at the direction of the arrow, and that's showing us which way the force is going. So our lines of force are moving out that way. Now, let's go back to our spheres over here. Okay. What is going to happen now if we actually bring these together? Each one of these electrons is going to be happy to be reunited with where they got rubbed off from. Theoretically, pretend, right? They could have been rubbed off anywhere, but it doesn't matter. So each one of these electrons is going to hop into a box over there, right? It's going to hop into a box. So each one is going to essentially, let's just do it, cancel each other out, isn't it? So 10 of them are going to cancel out, and they're going to hop into the box here, right? So over here we had a plus and a minus. We've now got 0, haven't we? Because they've cancelled each other out. So when they've touched, when they've touched each other, all right, what have we got? All right, I'm going to just remove this character over here, and we'll come back to some of those later. Let's just have a look. Okay. What have we done? We have put these two together. Now, all right. Now what are we left with? Okay. What has happened is that 10 is cancelled out. So we are left with, we started off, remember, with 10 electrons plus 20, let's say, protons, which gives us a total of 10 protons. In other words, 10 positive areas. Well, what happens here is they spread out evenly, don't they? So we're going to get them around the surface of this as far as possible, and you can see that you're going to get 5 on this side and 5 on that side, because we're going to get all the positives going there as far as possible away from the others, and they're going to be spread. Now we move them apart from each other. What have we got? We've got plus 5, plus 5. Now what has happened is they are both positive, right? So we've got positive, positive, repulsion, like so. Okay? So what do? We just look at it logic. We say, what have we got? Have we got more positives than negatives? Therefore, the negatives will cancel out the spare space, leaving us with positives. If it's vice versa, if there's not enough parking garages for the electron to move in and close the door and become zero charge, then we're going to end up with a negative. We pull them apart and then they're going to repel each other. What would that look like? What would a negative look like? Let's have a look. We would have a sphere, negative, 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 right? Put in another negative charge there. So now what do we say? Well, we always draw from positive to negative. So these would be coming in like this, wouldn't they? You can see it's repelling. Okay. So once again, you can see the direction of the arrows. Somewhere there's a fictitious positive that it's coming out of. Okay. So what do? We look at the direction of the arrows, or we look at the charges and we say repulsion or attraction, and then we go always from positive to negative. Okay. Right. So in these charged spheres that we've got over there, we've got this situation of having a body and another body with a charge of a plus and a charge of a minus and a force of attraction between them. Right? Well, how big is this force? Well, surely we say to ourselves, well, hold on, if we take a magnet, okay, and we put it next to another magnet, we can actually feel the two pulling it towards each other or pushing, depending on which way we're going. But it depends on the strength of the magnet, doesn't it? I mean, if I took one here, right, one magnet, it's got a certain strength. But if I put it with all four, it's stronger. So it depends on how strong they are, doesn't it? Does this echo something from the past about Newton's universal law of gravitation? It's the same thing, isn't it? The force between these guys here is proportional to the charge, which is Q1, Q2. Right? In other words, how strong is the positive, how strong is the negative? Because the stronger they are, the more the force, right? And I don't know if you've ever trying to push magnets together, the force can become pretty powerful at the end of the day. So we can say it's proportional to Q1, Q2. And you're right, R squared comes back into it. You'll see this if you move on with physics further, engineering or physics at university. You'll see this law here. It applies to quite a lot of things, okay? So let us say, let's put them together now by constant proportionality, remember? Now in this case, they used K, Q1, Q2 over R squared. K, constant proportionality, but it looks the same as Newton's universal law of gravitation. And we're going to use it in many respects in the same way. The difference, however, is that Newton's law of gravitation was there's always an attraction between the two bodies. But in this case, there's attraction or repulsion, one or the other, right? So we're going to use this in ratio form, the same as we did with gravity. So when we look at the ratios, essentially we're recapping gravity as well. Although it's a new subject, we're going to be recapping it as gravity, right? How do we approach these things? Well, we approach it like this. We once again, okay, we put down, okay, we put down what we know, right? So if, for example, we're given a charge Q1 equal to, and we're given over here Q2 equal to some number, then we say, right, we know U. Do we know the distance, R? Yes, we do. And therefore, we know Q1, Q2, R. K is a constant. It's given. So therefore, we can work out the force. The last thing would be to say, is it a force of attraction or repulsion, right? You can use the signs of the charges. If this was a plus and this was a minus, we could use it. I prefer to just keep it out of it and just do it with the numbers. And in my mind, I say, okay, now is it attraction or repulsion, right? So you qualify and quantify it right at the end of the scenario. Okay. Let us now take, for example, one of these hypothetical situations where they tell us we have got a force between two charged bodies, Q1 and Q2. So they've told us there's a force between them. Now, we don't know if it's attraction or repulsion. We actually don't care because they've told us there's a force. So we say F1 is equal to K, Q1, Q2 over R squared. And yep, you got it. We're going to now change R, we're going to change Q1, Q2, and we're going to do exactly what we did with Newton's law. We're going to work out what is the ratio F2 to F1. Well, what do we say? Let's change it again like we did before. Let's put our new, let's say we double that one. So here's my new charge. This is going to be 2 times Q1, isn't it? I've doubled it. And on this case here, let's say we've left Q2 the same. Okay, so that is Q2. And let's then say that what we did with the distance between it, we quartered the radius. So let me go back and fill in this one. Okay, there's R between it over there. All right. We don't mind if it's attraction or repulsion. What do we now do? We now go and we look at this one and we say the red, let's keep it in red. The red scenario, F, let's say it's F2, is equal to K. Q1 is 2 times my original Q1 times Q2 didn't change over, okay, let me just make that clear, radius squared there, over 1/4 R squared. Okay. Now we simplify that and we see that that's going to be 2. A quarter squared is a 16th and it goes to the top, remember, over 1 times K, Q1, Q2 over R squared. And once again, okay, for those of you who did the gravity course with me, you will see there it is, right? So we say that that's then going to be equal to 32, if my arithmetic is correct, times F1. Right? So it's identical to the gravitational one. What do? We write down, we make a drawing of what we're starting with, the Q1, Q2s, and we write this in terms of those elements. And we just basically put it together and then rearrange, taking the numbers out to the front, which will leave us with F 1 in that side, exactly as we did with gravity. Okay. Now, that sort of sets the playing field for what we're going to do next. What we're going to do next in this is we're going to look at some examples of how do we calculate the force, particularly if they're perhaps not in a straight line. If we've got a dog leg or whatever the case might be, we're going to look at how to do those. So we're going to take some point charges and we're going to work out a resultant, right? And yep, F equals ma will come into it theoretically in a concept, but we're not going to apply it as such. But to be able to see what we're doing this for, it's kind of cool. That's what we're going to do in the next session. We're going to have a look, put some numbers to it, and just get a feel for what comes out of these.